Welcome, folks, to our Friday series, Cosmic Conversations. My name is Josh. I'm part of the Morrison Planetarium team at the California Academy of Sciences, and I am excited to be here with some of our experts from the Denver Museum of Nature and Science, with KaChun Yu and Bob Raynolds. We're going to be talking about some of the awesome stuff we see on planet Earth that tells us about the structure that's going on inside our planet, as well as where we see those things elsewhere in our solar system. So with that, I will hand it off. KaChun, can you tell us a little bit about the software we're using today? Okay, so we are looking at OpenSpace, checking out the surface of planet Earth. And while we're getting KaChun back on, looks like we are having a brief technical hiccup. We're going to be checking stuff out in the OpenSpace software, looking at the surface of planet Earth in the OpenSpace software, which allows us to see not only the cool details we have here on our planet in wonderful resolution, but also see some of the structures of planet Earth. Okay, so with that, I think KaChun is back.
Yep.
We should be
ready everyone.
to go. You want to tell us a little bit about OpenSpace?
Sure. It's a software that's sponsored and funded by NASA. It comes out of the American Museum of Natural History in New York, and both the Denver Museum of Nature and Science, which Bob and I are part of, as well as the California Academy of Sciences, are partners with the software in helping to develop it and to use it for programs like this. And we've been using it at Denver in some of our live streaming shows. And with that, I think since we have a action-packed program in not much time, I'm going to hand it over to Bob, who will be talking about the Earth, but then we'll be flying off to another world in the solar system at the end.
Great. Well, thanks, KaChun, and thanks you guys in California for helping us do this, and we're delighted to join you from Denver. I'm located just north of Denver in Longmont, and KaChun's down in Denver, and we're both in our respective homes, but we're delighted to be able to put this programming together and to share some of these wonderful views of the Earth. Our program today, we're interested in looking at the patterns of plate tectonics or continental drift as seen from above. And we'll start out with a view of the globe, and we might look at the South Atlantic just to get ourselves oriented. And the point to be made here is that if you look at this pattern, which many of you have done, I'm sure, on a globe, it's pretty easy to see the match between the margins of South America and Africa. And many people will have looked at that. I remember as a grade school child looking at a globe and saying, gosh, it looks like those things must fit together. And then once you get the bathymetry of the ocean, you'll see there's a mid-ocean ridge. We call it the Mid-Atlantic Ridge in this case. And it certainly makes an even more compelling story when you see that there's a symmetry about not only the margins of the continents, but also the water depths in the ocean. And it turns out that the Mid-Atlantic Ridge is the place where drifting or rifting is taking place, and those continental masses indeed are moving apart. We're going to now go over to, we're going to cross Africa, and we're setting this up so we'll give an illustration of how continental drift happens in places where it's really pretty easy to see it from space. And then we're going to come across to the North American plate, and we're going to work our way to California. So at the end of our Earth views, we'll be looking at California. But we're going to start here with this view of the Red Sea. And just like you saw in the South Atlantic, I think you can appreciate that the margins of the Red Sea are pretty symmetrical. And actually, as a graduate student, I had an exercise where we had maps of the Red Sea, and we used scissors, and we cut the thing apart and practice sticking it back together using literally cutting the map and gluing it back together. And it worked pretty well. Of course, today we'd do it digitally, we'd be more sophisticated, but the net effect is similar. As we move up the Red Sea, you can see there are two gulfs at the north end. The Gulf of Suez is straight ahead, and the Gulf of Aqaba is to the right, and the Sinai Peninsula is between the two. And I want to show a model here. Let's back up a little bit, KaChun, before we get too deeply into this, of the way this whole system is working. Just sort of an overview. And you've got the Nile River, the Nile Delta, the Mediterranean, Cyprus there in the central part of the scene. But if we look at the whole Arabian Peninsula, here we'll get it sort of centered. You can appreciate that the Red Sea is extending. We just talked about that. And the net effect on the other side of the system is compression. So you've got pulling apart on one side and pushing together on the other. So the Persian Gulf area on the right is compressing. And I have a little block diagram of this, which I'll try to show here. I'm going to bring it up so that you guys can see it. And in principle, I've just cut this out of a piece of paper, but you can see the Arabian Peninsula there with the arrows on it, and I can move it with a sophisticated tool here. And you can get a feeling for how it's the Red Sea's opening, and it's crashing into the Zagros Mountains. And then there's a strike-slip fault with a red stripe on it over near the Dead Sea. So you get that picture, and now we're going to go look at it from space. So here, as we zoom into the north end of the Red Sea, the Gulf of Aqaba is a strike-slip zone. The Gulf of Suez is pulled apart a little bit, but it's stopped in the Miocene. And then the motion is now taken up almost entirely on the Gulf of Aqaba. And the Gulf of Aqaba is a narrow gulf, as you can see there. It comes in, it's got the Sinai Peninsula on the left, it's got the Saudi Arabia on the right. And as we head up to the north end of the of this Gulf, you'll come to the town of Aqaba, which some of you will remember from Lawrence of Arabia. He actually conquered the town by surprising people by coming in overland on his camels up at the very north end of the Gulf of Aqaba here. The town of Aqaba is there. Now, as we go north up along this trend, we're going to be following what's really a strike-slip fault. So plates have places where they pull apart, they have places where they push together, and then they have places where they slide side by side. And those of you in California are familiar with that, but this is a place where it's sliding side by side. The area on the right-hand side is moving north or up, north away from us relative to the side on the left. And as we come up, we're passing Petra, we've got Jordan on the right, and we're going to come up here to the southern end of the Dead Sea, and you'll see they're evaporating the salty water just like they do in the south side of the bay in near San Jose. And they're the petrochemical facilities that are benefiting from the salt here from the Dead Sea. The Dead Sea, as you know, is the lowest place on the surface of the Earth. It's in this, there's an area in the strike-slip fault here where there's a sort of jag in the pattern netting the result of a very high subsidence rate, tectonic subsidence rate. So there's a very low area here, well below sea level, and the level of the Dead Sea is also falling. It used to be falling about 1 meter a year. So the lowest point on Earth was going down about 1 meter a year. I think it probably still is because there's limited amount of water coming in. And of course, there's huge amounts of evaporation in this area. The primary source of water into the Dead Sea is the Jordan River, which we're coming up to right here. You can see the mouth of the Jordan River. It's feeding down into the Dead Sea. There's not much water in this river anymore because it's primarily used for irrigation, as you can see on both sides of the river. It's coming, flowing down out of the Lake Galilee, which is coming up on the horizon. And again, limited water. This is an area that's tremendously water starved, and limited water resources, very effective recycling going on. But the linear pattern, you see sort of a linear trend as we head up towards the Sea of Galilee or the Lake Galilee. That's the strike-slip fault, which is a plate boundary between, in this case, the Arabian plate on the right, and what we'd have would be we might call it the African or the European plate on the left. Now, what happens in the territory we're coming up in towards Lebanon and Syria, and here there's a big arcuate fold belt called the Palmyran Folds, and they swing across. We're near Damascus now. These are swinging across to the right, to the east, and we'll eventually maybe back out a teeny bit, KaChun, so we'll get the overview. We'll cross the Tigris and Euphrates rivers, and we'll be coming in towards the area of the Persian Gulf. So up ahead is the Euphrates first, and then the Tigris up in the distance. Again, very arid ground. These waters come out of Turkey. They flow into Iraq, And we've got Baghdad sort of in the middle of the scene here. And as we start to see the Persian Gulf on the right, we see the fold belt now on the left-hand side of the screen. And these folds are magnificently well exposed. And again, one of the reasons for using this area as a teaching tool, as you extend in the Red Sea, you compress over on this side of the system. And this is the Zagros mountain chain, a very interesting and beautiful mountain chain. And it's got fabulous exposures of these are called anticlines. There's places where there's salt coming up. There's some salt glaciers. We might just KaChun fly over some salt glaciers, and then we're heading further out. We could back out a little bit just to keep our geometry good. So let's back up and just make sure everyone's seeing the Zagros Mountains nicely. You've got the Persian Gulf, the delta of the Tigris and Euphrates there, and this big folded belt. You'll see the fold belt there on the north side or the east side of the Persian Gulf. So the basic picture is the material on the lower left is moving to the right, and you've got extension in the Red Sea, compression in the Zagros Mountains. Now we can carry these thoughts over. Let's go over to, we'll cross the Makran range and we'll look just quickly at Pakistan and Afghanistan. And I'm doing this again to sort of set us up for our studies in North America in a couple of minutes. So you've got the green ground on the right is Pakistan and India. The gray ground or brown in the middle is Afghanistan. And there's a big north-south feature that separates Pakistan from Afghanistan. And that, again, is a plate boundary. It's called the Chaman Fault. It's a place where there's a strike-slip motion with the right-hand side moving north and the left-hand side moving relatively south. And you'll see the linear trends in the central part of the screen here. And that's called the Chaman Fault. It's a very active fault, deforming today. There's some folding going on the right, which is the Suleiman Range. that active strike-slip fault is the boundary between the Pakistan-India plate and Afghanistan. Afghanistan is actually being squeezed out to the left. We call it escape tectonics, and it's being pushed way out to the left. The whole system, of course, is part of the greater Himalayan range, and you'll see coming up, we might just get a quick view of the Himalayas before we head back to North America. So we're looking at the Pamirs, the Karakorams, K2, Nanga Parbat. Famous mountains are right there, snow-capped ahead of you. The Peshawar Basin, in the distance, the Kashmir Basin, the frontier between Pakistan and India, and up to the north would be Tibet. But I think in the interest of time, we've got to keep moving. And so let's go back to, we'll back out a little bit. We can do a whole program on the Himalayas sometime. It's a fleeting glance, but a wonderful place. The Tarim Basin, the Tibetan Plateau. But we're going to pull ourselves back home. And I now want to look at the North American plate in toto, meaning in all, and ask ourselves, well, where are the plate boundaries or the margins of these semi-rigid plates in North America? And we have fun doing this with students, and we've done this many times with our audiences at the Denver Museum. If we look at this view of North America, and I ask you where are the plate margins, we can see if anybody's guessing where the plate margins are. But on the right-hand side or the east side, where do you think the plate margin is on the right side of the North American plate? And I'm seeing a limited number of guesses coming in on the chat, but Mary's probably seeing more of them. The answer, I'll just quickly give it away, just because we've got to get to California, but the answer is the eastern side, the plate boundary is the mid-Atlantic ridge, so way out in the middle of the ocean. And you can see that if you go to Iceland, it comes up above water level. So the plate margin on the east side, or on the right side of the North American plate, is the mid-Atlantic ridge. And then on the west side, we'll go scooting over to the Gulf of California. And of course, you guys in California are much more familiar with this side of it. And I hope you know that your plate margin out here is actually the San Andreas Fault. So we're going to take the next few minutes to look at the geology and geometry of the San Andreas. It originates down in the Gulf of California, Sea of Cortez, which is an obliquely extending ocean basin, a lot like the Red Sea. The patterns, maybe it's not so clear in terms of fitting the sides back together again, probably because it's so obliquely extending, but a narrow, very young ocean basin, the Sea of Cortez. If we go up to the north end of it, of course, the Colorado River's coming in there, and we've got Baja on the left, and we've got northern Mexico on the right, and we're coming up towards the U.S.-Mexico border, and you can see the Salton Sea is sort of a landmark up ahead, and you'll see the fertile ground, irrigated, the Imperial Valley, the sort of a breadbasket area there. As we cross the Salton Sea, we come up north, we're heading up towards the Mojave Desert. We've got the Los Angeles area on the left, the LA Basin, and then we've got the Mojave Desert in the center. And here, very interesting geology. There's a volcano that has been rent asunder by the San Andreas Fault. And it's called the NNX volcano, and it's the right-hand side of it is right near that little lake that's in the center of the screen. There's a zone there full of volcanic rock that's very distinctive, and it's been studied hard by geologists. The trend, the linear trend in the middle of the screen, north-south, is the San Andreas Fault. But right in this area, near some of this irrigation, are the NNX volcanics. And I point this out to you because we're going to drive north along the fault, and we're going to find the other side of the volcano that's been dragged a long ways to the north. We'll get there in a few minutes. But here you can see the linear trends. We're going to scoot up north along it. San Andreas is defined by a wide variety of geomorphic features, which include ridges and linear valleys. And it took a long time for geologists to realize how much offset has been present on this huge fault. But after the 1906 earthquake, a lot of people studied the San Andreas, and there was early speculation that it was a huge, very long fault. But the significance of the offset was really nailed down by people studying the geology on both sides of this feature, and we'll get to that when we get up a little bit further north. But we've got to scoop north here. We're crossing the Carrizo Plains, and we're going to head up past, we've got to move up so we get up near Paso Robles, and we're going to see the Monterey Bay coming up a little bit in a minute. But as we get up closer towards the town of Hollister, and we've got to pulling ourselves north here, we're going to come up to a place called the Pinnacles, which is some of these green mountains that are starting to be visible here on the left-hand side. And the Pinnacles volcanics actually represent the other side of that volcano that we talked about earlier. And so we've got one side of the volcano on the left-hand side of the fault, the other side of the volcano on the right-hand side, and the offset is about 200 miles. And geologists can date the volcanic rocks, and the volcano is about 23 million years old, and it's about 200 miles separated by the fault. And so when you do the arithmetic, it comes out to about 1/2 inch per year of offset, and that's the number that we think is about right. In fact, we can measure it using GPS. So we use detailed measurements from GPS, and they corroborate the geological observations. We've got to continue north here, KaChun, so that we can get ourselves
Bob,
up.
we got a real quick question. Was there more volcanic activity in Earth's past than there was today?
Well, that's a good question about the volcanoes. We do see times in the Earth's past when there was more volcanic activity. For example, the Columbia River basalt flows up in Washington and Oregon would represent a time of great volcanic outpouring. But there's a pretty general rhythm of volcanism that's very much still active today. And every single year, there's not necessarily a big volcanic eruption, but volcanologists are keenly aware that there's a lot of activity. We've got the Salinas Basin here in the foreground. The San Andreas Fault's actually a little bit to the right. But there's a whole string of faults that are parallel to the San Andreas. The San Andreas is just the currently active strand of this plate boundary. And for those of you who live in Berkeley or know about the fault underneath the Berkeley Stadium, it's one of the strands of the fault. And down here, there's the Nacimiento Fault, which is parallel to the San Andreas. Now we're coming up to the southern Bay Area. We just crossed over Hollister, where the fault is moving every day a little bit. and now we're in the Southern Bay Area, San Jose and Cupertino and whatnot. And here the fault is stuck and hasn't moved since 1906. And it's built up a lot of pent-up energy strain because of the half-inch movement per year. And so the Bay Area is in a pretty challenging situation where the geologists know there's been a tremendous amount of buildup of stress, and it will someday release. So we're going to come in, fly in low over the Cal Academy, and then we're going to head ourselves up towards we'll go up towards Point Reyes, and then we'll transition to KaChun. So we're just looking at the San Francisco area here, and of course, those of you who are at home in this area will recognize the roof of the Cal Academy right there. Interesting topography on the roof. I think what the dome sticks up, is that something that's visible on the roof of the Cal Academy? I don't know if
we got all sorts of weird stuff up on our roof.
Yeah.
Probably whale bones.
Okay, well, there's your roof. So we're just flying over the roof of the Cal Academy, and just to keep our vantage point, we'll take one last look at the San Andreas system just offshore from the Golden Gate Bridge, over there towards Point Reyes. And you'll see a beautiful linear pattern, Point Reyes on the left, and then that goes right up along Tamales Bay, and that'd be the, again, trace of the San Andreas Fault. But I think in the interest of time, we've just, I'll quickly recap. We started with the symmetry seen in the South Atlantic and the Red Sea. We looked at plates that are either pulling apart or pushing together, or in the case of the San Andreas Fault, sliding side by side. And those are the patterns that are so common on the planet Earth. And now, KaChun, we'll just turn it over to you for a sortie.
Yeah, thank you very much, Bob. So what we're going to do is we're going to fly to another world where we see examples of tectonics, although there are no other planets or moons in our solar system that have plate tectonics like the Earth does. But some of you might be trying to guess where we are going. And let me see if I can get there quickly. We're in fact heading to the Jovian system. Here's the planet Jupiter. And we're headed to one of its moons. We're headed to the moon Europa, which is the smallest of the large Galilean moons. Europa is slightly smaller than our moon. But what's really unique about it is that there is an icy shell made up of water ice that completely covers the surface. And there are very few craters, but what we see are numerous cracks on the surface. And so what we think is going on is that there is a subsurface ocean of water underneath that thick shell of ice. And this water causes these the hard shell to be more fluid and to move and to crack, and the water can well up from underneath. And as Bob says, there are a lot of features on the Earth that we understand by comparing them to other parts. And in fact, planetary geologists often start studying the Earth to understand how similar processes can work on other worlds. And we see the same sorts of faulting and behavior on Europa as we do on the Earth. And let's see if I can find one of these features. We're actually going to a somewhat low resolution patch of the planet, but all these cracks are places where the surface has broken and spread apart. So this idea of extension of the surface spreading apart is something that we see on Europa, just like we do on the Earth. And here you see kind of this linear dark band that runs across horizontally. It kind of curves horizontally. It looks kind of low res, but I can actually bring up a higher resolution image. On the left is actually that band at high resolution. And you can see that on the north and south sides of the band, there are similar features, just like, and so this is very similar to the Red Sea that we had seen before. And the researchers have basically, I think using Photoshop, erased that band. And then just like what Bob was talking about, taking pieces of paper, cutting them apart and smushing them back together, the picture on the left shows you what happens when you smush that back together. You see the two halves of Europa fit together almost perfectly. There are other faults that cross over from one side of that band to the other. And so here is an example of extension that takes place on a completely different world. And,
it's pretty cool to think about high-tech
so we
stuff
know
like NASA.
that Europa is a place where the entire surface of the moon is spreading apart. We actually don't have any good evidence of it compressing like we do on the Earth. So Europa is just a really bizarre place, but we're seeing very similar types of dynamics and tectonics as we do on the Earth, but in a completely strange and otherworldly environment. And so with that, that's it for me. And I think Bob and I are both happy to take questions from the audience.
Well,
Aaron,
I know I've
Josh,
got a question.
Do we have any really burning questions that you think we can help answer?
So one question that came up, I know I have, is it's strange to think about a really high-tech process like...
Just one other thing while we're waiting on them, I don't hear anyone, is fly back down to Europa. And there are actually lots of other examples of places where you see faults coming in. So here, if I zoom in, here, this dark streak that kind of runs diagonally through the center of the screen, that's another example where that dark band is a place where the ice has pushed the surface apart, and then there are two horizontal bands that have come up.
You haven't heard the host.
Oh.
Okay, well, KaChun seems to be working out some tech hiccups on his side. No big deal. As soon as he's back on, we can add him back in. There we go.
Yeah, sorry about that. It looks like frozen.
So a question I have is, it's always kind of strange to think about something as high-tech as satellite photography on another planet happening, and then someone going in Photoshop or cutting out the piece of paper and sticking it together. Are there other instances of tech like this being used where you've got something very high-tech butting up against something that seems very, very low-tech?
I think, I mean, Europa is a pretty unique example just because the surface is so dynamic. This is a relatively young surface, and we think there are cracks that are forming or being reinforced on an orbital period cycle. Europa orbits Jupiter every, I think, 80 hours or so. And so, these cracks are changing very dynamically on very short time scales. The evidence for tectonics on the other worlds, there's a lot less of that. So Mars nor Venus, neither of them have plate tectonics as we know it. And so even though we know we have evidence that Venus might be volcanically active, and there are Mars quakes that we are detecting, they don't present the same types of tectonics as we see on Europa. That's a good question.
So is there a specific planetary body that you find most interesting, Bob?
Well, of course, my favorite planet is the Earth. I'm a geologist, and so I find that there's infinite complexity and variety on the Earth. But one of the key things to underline here is that we, as geologists, we recognize patterns. And the question earlier that Josh asked about high-tech, low-tech, the geologists are a pretty good example of people that use a huge variety of tools. And some of it is sophisticated computers with computer modeling and plate reconstructions. And others are just out walking around in the field looking at rocks. And for example, if you're in the Bay Area, it's wonderful to go out hiking on the hills around the Bay Area, and you'll find amazing rock types in the hills. You'll find bits of oceanic crust that have been squeezed up along the plate margin. It's called a melange, or a mixed up zone of rocks that characterize the Bay Area geology. And there's beautiful things to be seen. And you can see it just by taking a walk. So very low tech. And then you can fit it into something more sophisticated, like our story about continental drift and plate tectonics.
Well, you gave a great shout out to my absolute favorite park, which is Pinnacle. So I give you a big thumbs up for that. Dan St. John wants to know, what about the Mississippi River fault?
Well, the Mississippi River flows down an ancient fault system which is very old, goes back into the Mesozoic, maybe even earlier, and it's been reactivated along something called the New Madrid Fault, where there was a big earthquake back in the 1800s, and which is certainly has the potential of having another earthquake today. A poorly understood fault in many ways. It's not in a plate margin situation today. It may have been in the past, but today the Mississippi River system is flowing down. The trough is called an allocogen. There's all kinds of fancy names for things, but it's a beautiful, long-lived river system guided by a very ancient fault system that is running up and down the axis where the Mississippi goes into the Gulf of Mexico.
There's some beautiful stuff you're showing us, KaChun. It's always so cool to pick out those geo features in satellite photography. But the same question for you. Do you have a favorite planetary body?
Well, I'm actually not a planetary scientist. I'm an astronomer, so I study star formation. And so I don't come at this from a research perspective, but having worked with planetarium software for close to 20 years now, and having developed a lot of it and using a lot of these tools for our programs, I think, from a more of a layperson's perspective and enthusiasm, I really enjoy the Earth. And having done programs above for over 10 years, I've gotten a real appreciation of the beauty of planet Earth from space. And being able to explore it with these tools that we have is pretty amazing. The fact that we can see imagery that was taken from satellites orbiting a couple hundred miles overhead and zooming down to surface details that would have been unheard of, a decade or two ago.
Absolutely.
Yeah, we have a program, for example, Earth as Art. So we're putting it together for the Denver Museum, where we're just going to treat the Earth as our artist template, and we're going to look at a variety of fascinating patterns that, of course, have geological underpinnings, but have their own aesthetic beauty just as patterns and images.
Well, I'd be remiss if I didn't say there's a shout-out opportunity here. If you folks like this imagery and you want to check it out at home, one of the coolest things about OpenSpace is you can download it and fly around just like KaChun is doing. Maybe not as practiced as him, but if you give yourself some time, you'll get there. We had a question from Bing. Why do quakes in some part of the world, like Chile or Alaska or the Middle East, seem so much more violent than our lesser quakes in California?
Well, I think that you've got to appreciate that the action in plate tectonics is at the plate margins. And so different plate margins have different stickinesses, if you can think about it that way. So, for example, if you live in Hollister, just south of San Jose, there are little tiny earthquakes every day because the San Andreas Fault is moving bit by bit every day. But in the San Francisco Bay Area and down in the Los Angeles area, the fault has been stuck for over 100 years in the case of the San Francisco Bay. And when that fault moves, it's going to be big. It's going to be a magnitude 7+ fault earthquake. So different plate margins have different styles of earthquakes, and the challenge for us as geologists and seismologists and people studying the Earth is to recognize that our time scale as humans is short because our lifespan is short, and geology is long and vast and huge in time. So over geological time frames, these plate margins are consistently active, dynamically moving with lots and lots of earthquakes. On a human time scale, it might be that for a whole lifetime, there's no earthquake at a given point. And then other times there might be several earthquakes in one lifetime.
We have a fun planetarium show talking about those exact ideas. But I think we've hit our time limit. Thank you both for joining us here for our Cosmic Conversations. Thank you to Mary for being our super producer in the background. It's been a real joy. Do you have any parting words for our folks? Okay.
Well, come to Denver.
Yeah, come to Denver. Check out the rocks there. I'm sure you got cool stuff at your museum.
And come check out our programs online, too. We've been posting them to YouTube.
Great stuff on the Denver Museum YouTube channel if you folks want to check it out. On behalf of myself and Morrison Planetarium, thank you all for letting us into your homes to tune in for this special broadcast. We hope to see you at subsequent weeks' Cosmic Conversations. We've got cool programs happening on Tuesday, Wednesday, and Thursdays as well. But on behalf of myself and all of us and OpenSpace, thank you for joining us. Have a great rest of your day.
Thanks, everybody.
Bye-bye.